What does it really mean for an AI to think? Today, we're diving deep into algorithms define decision velocity. Every digital system is an algorithm. From recommendation engines to autonomous vehicles, logic orchestrates action. Data volume grows 10 times every 3 years. Compute cycles remain bounded. The bottleneck is no longer hardware, it's algorithmic adaptability. Strategic imperative: algorithms must evolve as fast as the environments they model. But here's where it gets interesting: static logic breaks under dynamic load. Traditional algorithms are frozen at deployment. They assume stationary inputs, fixed objectives, and known edge cases. Real world systems drift, consumer behavior shifts, fraud patterns mutate, infrastructure degrades. Retraining cycles take weeks. Redeployment is manual, brittle, and risk laden. Current approach: overfitting to the past, underserving the present. So, what's the real problem? Let's talk about the root cause: separation of design and operation. Algorithms are crafted offline by humans, then handed to runtime. No feedback loop exists between execution and logic. Monitoring tells you something failed. It doesn't tell you which rule broke or how to fix it. The gap: logic that cannot introspect, reweight, or restructure itself. Consequence: every algorithm becomes progressively less optimal the moment it goes live. This raises a critical question: breakthrough, self-recompiling algorithmic kernels. We introduce continuous algorithmic optimization, CAO, a kernel that treats its own control flow graph as a learnable parameter. Using metagradients and just-in-time symbolic rewriting, logic restructures under load. Safe execution boundaries guarantee correctness while adaptation proceeds. The algorithm becomes a living system, not a static artifact. Now let's zoom in on the adaptive kernel platform. An operating system for algorithms, runtime layer, instruments execution paths, collects decision provenance. Optimization engine evaluates logic graphs against live objectives, proposes rewrites. Sandbox validates candidate kernels at shadow traffic before promotion. Kernel registry: versioned, auditable, rollback capable. Here's something most people overlook: system components. Perception mesh stream signals, data drift, latency spikes, fairness deviations, resource contention. Recompilation core symbolic AI searches program space for equivalent, but faster, fairer, the more robust variants. Policy guard encodes safety invariants, regulatory constraints, and cost ceilings. Overrides invalid rewrites. Execution fabric hot swaps kernels without downtime. Maintains state consistency. Think about this for a second. Kernel recompilation workflow. Deploy algorithm runs with current logic graph. Sense performance surfaces, detect divergence from objective landscape. Recompile core proposes N candidate graphs. Shadow evaluation ranks them. Certify policy guard verifies invariance, resource bounds, compliance. Activate live hot swap to winning kernel. Metric stream confirms improvement. Cycle time under 300 millis. And this is where things get complex: architecture, layered adaptive stack, application layer, business logic, APIs, user experience, adaptive kernel layer, self-optimizing algorithm instances. Recompilation and policy engine graph search, safety enforcement, perception and telemetry mesh real-time signal ingestion execution, substrate Kubernetes, serverless bare metal edge, each layer isolates concern. The kernel layer is the first to close the design operation loop. But here's where it gets interesting: impact. From reactive to self-healing. Latency reduction 40-60% in decision pipelines measured at P99, drift resilience. Models stay within 2% of optimal accuracy across 90 days without manual retraining. Operational overhead. Algorithm management FTE reduced by 70%. Incident recovery. Kernel self-rollback resolves 83% of degradation events before on-call pages. Cost compute adaptively rebalances, lowering cloud spend by 30% during low signal periods. So what's the real problem? Let's talk about comparisons. Then versus now. Before CAO static code, periodic retrains, manual A/B testing, mean time to repair 4 hours, rule drift unnoticed for days, engineering bottleneck with CAO continuously recompiling graphs, automated shadow certification, self-healing in 3 minutes. Anomaly. Surface instant restructure. Algorithm teams shift to objective design. This raises a critical question: the next horizon. Algorithms that design algorithms. Today, CAO optimizes within a given logic grammar. Next, kernels that synthesize novel algorithm families. Generative program search discovers control structures unseen by humans. Result: algorithms that achieve state-of-the-art on tasks without prior art. The boundary between algorithm design and algorithm execution disappears. Now let's zoom in on join the continuous compute era. CAO SDK available for Python, Rust, and WebAssembly. Integrates with existing ML stacks, feature stores, and decision engines. Documentation, sandbox environments, and benchmark suites live now. Early partners seeing deployment in fraud detection, autonomous driving, and real-time pricing. Algorithms will never be static again.